Welcome to Mathland. Let's move on to question 11.2. We are given a complex diagram featuring a cyclic quadrilateral, parallel lines WE and PQ, and a tangent line QS. Let's build the geometry. Question 11.2.1. Prove PR equals PW times Q, R over QE. By fading the background and isolating the large triangle PQR, we can clearly see the parallel lines. Using the proportionality theorem, since WE is parallel to PQ, we get PR over PW equals QR over QE. Cross-multiplying and solving for PR gives us our exact proof. Question 11.2.2. If triangle PQZ is similar to triangle RQP, prove PQ squared equals RQ times QZ. First, let's draw a line PZ to reveal the triangles. Because they are similar, the ratio of their corresponding sides must be equal. Cross-multiplying PQ over RQ equals QZ over QP instantly gives us PQ squared equals RQ times QZ. Question 11.2.3. Prove triangle QSZ is similar to triangle QRS. Looking at just these two triangles, they share a common angle at Q. Next, angle QSZ equals angle SRQ due to the tangent chord theorem. Because two angles are equal, the third pair of angles must also be equal. Therefore, the triangles are similar by angle. Question 11.2.4. Prove PQ equals QS. From our previous similarity proof, we can deduce that QS squared equals QR times QZ. But from question 11.2.2, we already know that PQ squared also equals RQ times QZ. Since both squares equal the exact same product, PQ squared must equal QS squared, meaning PQ equals QS. Finally, question 11.2.5. This is a grand substitution. First, we rearrange the equation from the very first question to isolate PW. Next, we use the similar triangles from question 2 to express PR. We substitute this PR expression into our PW equation. Notice how the QR terms perfectly cancel each other out on the top and bottom. Finally, we substitute PQ with the square root of QR times QZ, which leads us to the final proven equation.